Thanks to the organizers for giving me the opportunity to give a talk here. So as you can see, I'm going to talk about some eigenvalues of some matrices. And let me start with a very basic definition of representation. So a representation is a pair rho comma v, where rho is going to be a group homomorphism from G to GLV. And for our purpose, V in fact will be a finite dimensional vector space over arbitrary, over a field of arbitrary characteristic. But our results will be mostly on characteristic 0. But again, we will be concerned with the irreducible representation, which is a representation where there is no obvious invariant subspace, G invariant subspaces. A simple notation. So mod G going to denote order of G, and OG will be denote order of G in G mod center of G. So the general problem which we are interested in is, so let rho v be a representation and G be an element of G. Then the general question is, what can we say about rho G, the matrix rho G? And the first question is, can we determine the Jordan normal form of rho G? In characteristic 0, in particular, we could ask, can we determine all eigenvalues with explicit multiplicities? As you can see, this is a too general problem to expect any concrete answer. So we will first restrict ourselves to irreducible representations. And in literature, there have been many restrictions of this problem have been considered. For example, one of them is the dimension is being very small or sometimes prime. Or you can assume that G does not lie in any proper normal subgroup, meaning the conjugacy class of G generates the whole group. Or G is an element of order prime power, or even just have prime order. And similarly, G or G prime is quasi-simple, and you can consider the characteristic of the field to be not a divisor of cardinality of G. And when the group is of Lie type, you could vary from whether it's a defining characteristic of the Lie type or it's different from it. And the other one is very important for us, which is one of our main question, which is that so the degree of the minimal polynomial is less than order of G, or more precisely OG, the order of G in G mod center of G. Or you could ask whether G has eigenvalue 1 or not, meaning rho G has eigenvalue 1 or not. Or you could ask any combinations of this question. And in particular, there is a very nice version on this, which is, can you determine all irreducible representations, or equivalently, you take a representation G and you say that a representation rho is unisingular if the matrix rho G has eigenvalue 1 for all G belong to G. And such representations are called unisingular representations. And a complete solution to this question, meaning you take any finite group and can you determine all unisingular representations of G. This is not even been done for many families of groups. In fact, there is a recent survey on this theory where the author Zaleski describes that there is only 2 families of groups considered for this question, meaning determining all unisingular representations, which is symmetric group and alternating group, which is due to me, Amri and Amrita. So there is a lot of progress needs to be made since it's been done only for 2 families of groups. Okay, so why are we doing this? There are many motivations to this, starting with linear algebra, geometry, arithmetic algebraic geometry, and game theory in group theory and so on. For example, I've seen an article recently, in May, in fact, now it's not really recent, which states that, showing that an element of a finite group has eigenvalue 1 gives you a sufficient condition for a closed flat manifold to be a manifold with some property called R infinity. I have no idea what's the property, but yeah, so there is applications like these. And of course, Kautz also has some problem motivated by some aspects of Galois theory and abelian varieties, which can be restated in our language, which is as follows, which is that you take a symplectic group with the base field having prime order, then can you describe all irreducible subgroups of it such that all elements in it has eigenvalue 1. Irreducible subgroup means there is a natural representation, right, which is f to the power 2n, and the subgroup has to act irreducibly on it. So at least for today, what we are going to do is solve this question for a specific group. So the question is, can we characterize all pairs rho G such that, which consisting of irreducible representations and elements of the group such that rho G has, the number of distinct eigenvalues of rho G is less than OG, where again OG denotes the order of G in G mod center of G. It's easy to see that the number of distinct eigenvalues of rho G will always be less than or equal to OG. That's just because when you raise G to the power OG, you'll get some element in the center of G, by definition of OG. And now if you apply rho on it, meaning the homomorphism, then you get rho G to the power OG and rho of T. But Schur's lemma tells us that this rho T have to be a scalar matrix. And now that tells you that this equation can have at most order of G many solutions, meaning if x is an eigenvalue, then x to the power OG is equal to lambda can have at most OG many solutions. That tells you that it's always less than or equal to OG. And the question asks, can you determine when it is less than that? And of course, the question, it's not nice for all the groups. For example, if you take cyclic group or abelian groups, you can see that they're all one-dimensional characters. So, it's always going to be less than OG typically. So the main objective is to ask this question for the groups which are close to being simple. For example, quasi-simple, or almost simple, or just simple. And what we do is we're going to consider the double cover of symmetric group. I'll explain what is that. And we will answer this question completely. So they are essentially, they are actually solution to this short exact sequence where the image of this Z2 has to be equal to the center of G, and the G prime, the commutator group of it, must contain plus and minus 1. And of course, G will surject into Sn. So you can easily see that the cardinality of G will always be 2 times n factorial. Okay. So let me give you make you more familiar with this double cover. So first, of course, our symmetric group is generated by n-1 transpositions, where SA is going to denote the transposition I and I plus 1. And of course, the transposition is going to have order 2, and the product of the successive transpositions will be the 3 cycle. So we'll have order 3, and disjoint transpositions will commute. So there are 2 solutions to the short exact sequence. The one is as follows. So now we have one more generator, which is of order 2 minus 1. And there is n-1 generators again, which are going to be analog of our transposition. And we are going to define again our transposition to have order 2 and successive, meaning the 3 cycles to have order 3. And now the refinement is the disjoint transpositions will anti-commute, meaning tk prime times tl prime is minus tl prime times tk prime. And there is one more group which is going to satisfy this, where now again we have the same set of generators, and our 2 cycles going to have order 4, and our 3 cycles going to have order 6, and again the same thing, the disjoint transposition is going to anti-commute. And thanks to Schur, who proved that there are only 2 solutions to the equation, to the short exact sequence which you have seen before, which are given by these two, and these two are non-isomorphic groups except when n equal to 6. And in particular, you call a representation of this double cover Sn tilde a spin if -1 acts as a minus identity on that representation. Okay, so now if we have a representation V, a spin representation V of Sn tilde, which takes Tj to Aj, a matrix, then we can take Tj prime, the generators of our first double cover, to I times Aj, and it's quite easy to verify the defining relations. So that will also tell you that we are going to get a spin representation for Sn tilde prime. So what I'm trying to say is that for every spin representation of Sn tilde, the same representation space is also going to give you a representation for Sn tilde prime. So in fact, the matrix, if you take any element in one, then the corresponding matrix for the other essentially going to differ by a scalar matrix. So we have now two non-isomorphic groups, though all the representation spaces are going to be equal. This is some new, thing. Okay, so in particular, it suffices to consider only one of the groups for our purpose because we are interested in only the minimal polynomials of it. So like Schur and Stembridge, we are going to fix our G to be the second double cover, which is these generators and all, transposition 3 cycles are going to have order 4 and 6 respectively, and disjoint cycle is going to anti-commute. Okay, so first, for our purpose, we have to consider, we have to take all representations of Sn tilde and all elements in it, and we consider the corresponding matrix and check what's the minimal polynomial of it. Of course, if you have, if the -1 in Sn tilde going to act as identity, then you can see that is in fact will factor through Sn, meaning that's in fact just a representation of Sn. And so it's just suffice to see what happens for irreducible representation of Sn. But that's been done. Thanks to a lot of work have been done by starting with Klatchko 1956 and then Swanson at 18. Okay, it's 1974 by that. And Yang and Starletow and me and Amrita and Amri. Finally, Starletow who answered this question completely, meaning you take any irreducible representation of symmetric group and any permutation in it, then the corresponding matrix, we know what's the minimal polynomial of the corresponding matrix. So we only consider a spin representations of it, meaning -1 gonna act as minus identity. Okay. So a bit of notation, and so now we'll tell you what are all the irreducible spin representation of Sn tilde. So the first dPn gonna denote strict partitions of n, meaning all parts of it are distinct, and dPn plus gonna denote strict partitions with even number of even parts, and other denotes the same strict partition with odd number of even parts, and On gonna denote set of all partitions with odd parts. So the theorem due to Schur is that all irreducible spin representation of the double covers indexed by strict partitions of n, and in fact for each strict partition in dPn plus, meaning even number of even parts, there is a unique irreducible spin representation, and for each lambda belong to dPn minus, there is a two inequivalent irreducible representations, which is phi lambda plus and phi lambda minus. Okay, so what are all the conjugacy classes? Strict partition, those are, which has where all parts are distinct. Yeah. Okay, so what are all the conjugacy class of Sn tilde? So we can take a conjugacy class in Sn and we consider its pullback, which is, so by basic group theory will tell you that can remain as a conjugacy class or can split as a union of two conjugacy classes of equal size. Again, Schur already proved that when mu belong to On, when it has odd parts, this inverse image of the conjugacy class C mu is going to be union of two conjugacy classes. And for the partitions in dPn minus, also the inverse image of this conjugacy class is going to be union of two. And all other in cases, it's going to remain as a single conjugacy class. Nice. And I mean, there is in fact only one result towards this direction have been done, which is due to Zaleski, who shown that if you take an element of prime order and take any spin representation of it, then the minimal polynomial will always be x to the power p minus 1, except in a very few cases when the prime is 2 and it's just S2 and the prime is 3. There is one infinite family when lambda equal to n. That's also called as a basic spin representation. I'll tell you what's the explicit minimal polynomial, but sorry. So for p equal to 3 and p equal to 5, there is a basic spin representation which will give you where the corresponding minimal polynomial is not going to be x to the power p minus 1 is something which is a proper divisor of it. Okay, so what's the main theorem? So let lambda be any strict partition of it, meaning let's take any spin representation, irreducible spin representation, and mu be any partition of n, meaning we take any element with cycle type mu. So by I mean cycle type, you first project into Sn and then see its cycle type. So, and now the claim is, or the theorem states that the rho lambda w mu has minimal polynomial x to the power L minus 1, where L is the order of G, except in the following very specific cases. The first one is, of course, our basic spin representation with the property that, where mu has 3 but not 5. So you can see that it's essentially, it's just reflected by a theorem of Zaleski. So mu contains 3 but not 5, and the remaining parts are not divisible by 3, where you have the minimal polynomial x to the power L minus 1 divided by x to the power L by 3 minus 1. And similarly, when lambda is, in the spin representation, but mu contains 5, it's exactly the opposite to the first case. And the third is, it contains both of these guys, but not the other, and remaining parts are not divisible by neither 3 or 5. And you have corresponding, it's very explicit. And finally, of course, there is an analog of our standard representation called basic standard spin representation, and that's again similar to the third one. Okay, so this is our first main theorem, which is a joint work with Amri, myself, and Alexei. So now let me talk about the later part of the paper, which is about a generally Navarra conjecture. First, let me talk about some other conjecture which you might have heard of. So let G be a finite group and P be a prime divisor of the cardinality of G. Then let this P prime of G denote set of all irreducible characters whose degree is not divisible by P. Then I think you might have all heard of what's called Mackay conjecture. So the Mackay conjecture states, okay, let N be a normalizer of a Silo P subgroup of G. Then the Mackay conjecture states that the set of all or cardinality of all the irreducible characters of G whose degree are co-prime to P is same as the number of irreducible characters of the normalizer of the Silo P subgroup whose degree is co-prime to P. And oh yeah, I must have told you. So even our So our results, everything is over C. Okay, so this is what the Mackay conjecture states, and it's interested by lot of researchers, which the number of pages, for example, goes to more than 400, which all going to contribute to the classification of finite simple group and also a background in quasi-simple groups. And finally, the last of the many steps have been done by Kebanes and Spath. But the story is not over. Now we have something called Rizzo. Rizzo and Morito made a new conjecture called Picky conjecture. which generalizes the Mackay conjecture very much. And again, I mean, so this Mackay conjecture took half a century, and I guess this may also take something, because this is much more generalized. I mean, this is about G and its normalizer, but this picky conjecture is about some elements called picky elements, which is more local. Okay, so that's Mackay conjecture. Now let's come back to Genelli conjecture, Genelli-Navarra conjecture. So you can see that the Mackay conjecture involves irreducible characters whose degree are co-prime to P. Now you can ask what about the irreducible characters whose degree is divisible by P? That's really not taken care of. So the conjecture states that if you have an irreducible character whose degree is divisible by P, then and assume that the restriction of the irreducible character to the Silo P subgroup contains a linear character, one-dimensional character, then the conjecture states that in fact it contains at least P distinct linear characters of P. And this is we proved this conjecture for our double covers, which is essentially a byproduct of our main theorem, which is not easy to see, but the construction maybe gives you the proof. Okay, so let me, again, it's not a proof, but let me describe what are all the combinatorial tools which is developed, which will be used. So a shifted Young diagram is essentially so if we take any strict partition, and a shifted Young diagram of a strict partition is a array of boxes where the first row is going to have lambda 1 boxes and the second row going to have lambda 2 boxes and so on. But each row is shifted I minus 1 units compared to the first row. For example, if you have a partition, strict partition 6, 4, 3, 1, then the corresponding shifted Young diagram will have 6 rows, 6 boxes in the first row, and the second row will start in the second column of the first row, and that will have 4 boxes and so on. And now we have, analog of, so now this is an analog of our Young diagram. Now we will have an analog of Young tableau as well. And this is going to involve 2 set of labels, which is 1 prime, so we have natural numbers 1 through 1, 2 and so on. And there is the prime letters as well. And the order is 1 prime is less than 1, less than 2 prime, less than 2 and so on. Okay, so what's the shifted tableau? So it's essentially, analog of a standard, semi-standard tableau, which is that you take an Young diagram of a partition, strict partition lambda, or shifted Young diagram of a shift partition lambda, and you fill with the entries in the set A prime, and with the following conditions. So the entries along the rows should be weakly increasing, and along the columns it should be strictly increasing. Sorry, my bad. Along the rows it should be weakly increasing as well as along the columns. And if you forget the unprimed letters and if you read along the columns, then it should be strictly increasing. And now if you forget the primed letters, if you forget the primed letters, if you forget the unprimed letters, then in the row, when you read along the rows, it should be strictly increasing. I think I'm messed up. Okay, and weight of a tableau is just you remove all the primes and you just read as the usual tableau. Okay, so this is one of the example of a shifted tableau. And there is also a shifted Little-Richardson rule, which is analog of a Little-Richardson rule. So you take 2 irreducible representations corresponding to a double cover of Sn and Sn cross Sm, and you induce to a bigger double cover, and that's described by some coefficients called shifted Little-Richardson coefficients. This is not the usual tensor product which we do for the Young subgroups, because here there is some anti-commutation. You can't see Sn tilde cross Sm tilde as a subgroup. there is, I mean, there is an anti-commission due to this disjoint transposition sampling. So just 30 seconds. So you can't see that. I mean, so there is this tensor product is in fact called the reduced Clifford tensor product. So it's not just V lambda tensor V mu. There is something which comes in the front, and this is and there is a analog of our Little Richardson rule, and finally this is the proportion. So the proof essentially is first to prove for the n cycles, and using this proportion, you can just use shifter Little Richardson rule, and that will amounts to give you a theorem for the n cycle, and the general case also follows by I mean, just using this repeated use of this shifter Little Richardson rule. And yeah, there are some future questions which is the main question to solve for, but the main question and to solve for the other interesting clips. Yeah, I guess that's, thanks. No. So for double cover of alternating group also the theorem, I mean, we proved the theorem, but just for the simplicity, we just shown for the, I mean, to the talk, we just considered the double cover symmetry. No, I mean, it's essentially, so it's all boils down to this proportion. So like I said, for the n cycle and the eigenvalues of it for the symmetric group, it's been done by Joshua, but his method uses asymptotics of characters thanks to many people who already developed. But for the double cover, apparently there is no such nice asymptotics. And I reproved his result using a proportion like this in the symmetric group, which only uses representation theory. So this has a nice analog in the double cover as well.
So you mean Swanson's result?
Yeah. So the analog is now a bit easier in, I mean, yeah, in the SN tilde. So we were able to manage, yeah.
Any other questions? If not, let's thank the speaker.
Thanks.